Hi, everybody. Welcome once again to my basement for another installment of CHY 113 lecture. I hope that you are all as excited to watch this lecture and learn about some more thermochemistry as I am to give it. And so last time we started delving deeper into thermochemistry, started looking at thermochemical reactions or thermochemical equations, and looking at the process of calorimetry, which is a way that we can obtain some of the thermochemical data. And so let's go ahead then and look at our warm-up questions from those topics. And so in this first problem, you just want to calculate the enthalpy change of a certain amount of, when a certain amount of ammonia reacts, and you're going to use the data from the thermochemical equation shown. So go ahead and pause the video now, and see what you can do. Hopefully you got negative 676 kilojoules. And so let's go ahead and work these problems out today as we go. And so in this problem here, and so one of the things we have to recognize just in general with thermochemical equations is that they provide just another conversion factor for us. So we know that every 1 mole of NH3 that reacts releases 176 kilojoules of energy. So there's our conversion factor. And so the first thing that we have to do is to take our given amount of NH3, 65.4 grams, and we're going to convert that over to moles just using our molar mass. Now that we are in moles, we're just going to use our conversion factor from our thermochemical equation, 176 kilojoules per every 1 mole of NH3. We plug that into our calculator and we come up with 676 kilojoules. Next is another thermochemical equation problem. And so here we're given the equation for the synthesis of water and the thermochemical data that goes along with it. However, in this question, you want to calculate the enthalpy change that's actually involved in the decomposition of water. So think about that. Think about what that means for our thermochemical equation and try to do the problem. I hope you got positive 1834 kilojoules. The big thing to remember here as we start out is that what we need to do first is to reverse our equation, because we are actually concerned with the decomposition of water for this particular problem. And so we're going to reverse our equation to represent the decomposition of water. When we reverse our equation, that reverses the sign of our enthalpy, which is going to be a fairly big deal for us that we're going to use quite a bit later in this lecture when we start talking about Hess's law. Now that we have our new thermochemical equation, though, now we can just do the same process that we used in the last problem. 115.6 grams of H2O divided by the molar mass in order to convert to moles. Now, though, in our step of actually using the energy, we also have to recognize that the 571.6 kilojoules of energy is from 2 moles of H2O from our balanced equation. And so that has to be reflected in our conversion factor here. 2 moles of H2O for the positive 571.6 kilojoules of energy. And so then we plug that in, including that 2, to get our positive 1834 kilojoules. Our last question is a calorimetry problem. Here you want to calculate the kilojoules per mole, the enthalpy of, you want to calculate the enthalpy of dissolution of KOH in units of kilojoules per mole. So again, recognize here that we're using our first law of thermodynamics, the law of conservation of energy. Using that information, see what you can come up with. I hope that you got negative 57.6 kilojoules per mole. And so what we have to start out with here is a recognition that the heat that the water gains is equal and opposite to the heat that the reaction loses. And so it's easy enough for us to calculate the heat that the water gained just by using our old friend Q. Oh, wow, sorry. That's better. Q equals MC delta T. So we know the mass of the water to be 100.0 grams. We know C of water. And our delta T of the water was positive 11.7 degrees C. And so that's going to give us 4895 joules, or 4.895 kilojoules. Now we do have to remember, though, that was our Q of the water. So the actual Q of the reaction is the opposite of that. And so it's negative 4.895 kilojoules. Now that's the amount of energy, though, when 4.77 grams of potassium hydroxide dissolves. We want the enthalpy in kilojoules per mole. So we need to take our 4.77 grams of potassium hydroxide and convert that over to moles. To see that we had 0.085 moles of KOH present. And so then we can take our negative 4.895 kilojoules, divide that by our moles for a final answer of negative 57.6 kilojoules per mole. This is, again, where it's very helpful for us. I don't know why I didn't put my negative inside the box there, and that's going to bug me if I don't fix it. There we go. Okay. This is another example, though, where it's helpful for us to think about our answer at the end and think about the sign of our answer. And so we knew in this case that the water warmed up. So the water gained energy without even thinking of numbers for right now. The water had to have gained energy because it warmed up. And the water is our surroundings. So the surroundings gained energy, which meant that the system, our reaction, had to have lost energy. When the system loses energy, that's an exothermic process, and we show that as having a negative sign for the heat, or a negative sign for that energy change. Because the system went from a higher energy state to a lower energy state. It lost energy. And so just take a second to think about that when you finish any sort of problem like this, because it would have been really easy to make some sort of mistake, maybe with your negative sign in this relationship. Maybe you did 23.0 minus 34.7 for your temperature, and so you might accidentally get a negative sign here. It's real easy to make mistakes with your signs, which is why it's so vital to just take those few seconds at the end and think about your answer. Does your answer make sense given the direction of energy flow? And so take that time to just think about it at the end to make sure that you're representing that energy flow direction correctly. All right. And so let's go ahead then and move on in our investigation of thermochemistry. And so today we're going to look at, again, just a little bit at calorimetry and enthalpy calculations. But then we're going to talk about two other ways to find the thermochemical data for a reaction. We're going to look at something called Hess's law and also heats of formation. Calorimetry works really well to find the energy of most reactions directly. And so as long as we can run a fairly simple reaction with the example we just looked at, as long as we can run something like a dissolution and measure, and then when the dissolving stops, the reaction's done, and it's a very simple process to observe and to measure. Or if we want to measure the enthalpy change associated with the exothermic reaction of adding an acid to a base, then it's a very again, a very simple process to look at. Incidentally, just as a unrelated side note, a scene in the movie Fight Club that always bothered me was when they were dumping lye, the very strong base, onto somebody's hand. And the solution to that was to add acid on top of that and neutralize the base. Holy crap, is that a bad idea? Acid-base reactions are extremely exothermic. They release a lot of energy. And so at that point, not only do you have a very strong base on your hand, but now you're going to add a very strong acid to it, which is dangerous in itself. But then you're going to have along with the corrosiveness of the base and the corrosiveness of the acid, now you have a very hot reaction taking place on your hand. Very bad idea. Water. And that's just sort of just a general lab safety guideline. Rinse things with water. I can't even describe how bad it would have been in that case in the movie if you had actually used acid there. Very bad idea. Anyway, back to calorimetry. And so for most reactions, for most sort of simple reactions that we can perform in a basic lab setting, calorimetry works great to find our thermochemical data. For reactions, however, that can't necessarily be controlled, or for whatever reason cannot be measured directly, we need another way. If it's not a reaction that we can simply perform in the lab, we need a different way to come up with the thermochemical data for that reaction. And that's what we're going to look at today, is a couple different methods to find that thermochemical data. And so one of the things that we have to recognize is that enthalpy, and in fact energy in general of a chemical reaction, but we're mostly concerned here with enthalpy. Enthalpy is what we call a state function. Now, the official definition here of a state function is that it's the property of a system that is determined by the state or condition of the system and not how it gets to that state. So in other words, enthalpy or a state function in general is some sort of property that is going to be the same regardless of how you get to it. And so this is a little bit different, but the same sort of idea. Imagine you're flying from Dayton, Ohio. Come on, mouse. You're flying from Dayton, Ohio to Los Angeles. Now, you could either fly directly, if you were lucky enough in this day and age to get a direct flight, or more likely, you're going to hit several hubs along the way. You might go to Atlanta, then to Salt Lake City, then to San Francisco, and then finally to Los Angeles. This would be, and one way to think of this is that as far as the locations are concerned, it's a state function because you still start in Dayton, you still end up in Los Angeles. And so it doesn't matter how you got there. Or think of it this way, the distance between Dayton and Los Angeles, the actual just straight distance between Dayton and Los Angeles is the exact same no matter how you go from one to the other. If you go directly, then that distance is the same as if you go very indirectly. The actual distance between the two does not change. A change in elevation, same exact idea. Let's say that I am climbing a mountain. There's our mountain. And if I'm going from one side of the mountain, here I am on one side of it, and I want to go to the other side of the mountain, then it doesn't matter if I go all the way up and over, Or am I lucky enough to maybe go up, find a peak bypass trail, and come over? The actual difference between the two is the same. What's not the same is maybe the energy that it took or the time that it took for me to do so. Those wouldn't be the same. But the actual difference, where I start and where I end, are identical. Same idea with a state function. It doesn't matter how you get there. The end property is the same. What this allows us to do is it allows us to apply lab measurements and some of the data that we might have to a real life situation. What we are able to do with this is we can measure the enthalpy of a reaction indirectly by using the enthalpy of the steps that lead to that same reaction. So in other words, as a very, very basic example, let's say that I want information about the reaction A makes D. So it's very, very general. And I want the enthalpy involved in that particular reaction. But for whatever reason, I can't measure this reaction in the lab. What I can do in the lab, however, is I might be able to measure A plus B makes C, and then C, let me back up. This might be a bad example. Nope, okay, I'm there. So A plus B maybe makes C, so that I can do, and then C breaks down into D plus B. And this I know, sorry, isn't real clear. I'm trying to make up an example off the cuff here, and it's not really working. But if I had some sort of process like this, then ultimately, and I knew the delta H of these, I could add them up, and it would get me eventually to the delta H of my overall reaction. Now, I'm sorry, I know that was a very poor example. And so let's just skip over that. That's why I shouldn't try to come up with examples off the cuff like that. So let's just move into Hess's law, because I think that'll be easier to see. And so Hess's law tells us that if a reaction is carried out in a series of steps, delta H for the overall reaction will be equal to the sum of the enthalpies of the individual steps. And so for reactions where we can't measure enthalpy directly, we might be able to measure the enthalpy of several steps that eventually get us there. We add all of those up, and that will give us the enthalpy for the reaction that we're looking for. And so for an example here, so carbon, a mole of carbon plus half a mole of oxygen can give us carbon monoxide. And so the synthesis of 1 mole of carbon monoxide, in other words, is expressed by this reaction here, or this equation. If we want the thermochemical data of this reaction, though, we run into a problem, because the carbon monoxide that's present will immediately react with any O2 that's still around to form CO2. And so this carbon monoxide that is formed immediately reacts with oxygen. And so that makes it impossible to directly measure the enthalpy of this reaction. We can't set up some sort of calorimetry experiment where we capture the energy and go through that process. We can't do this for this reaction because it's not going to stop here. This carbon monoxide will immediately react. And so that's a problem, at least as far as finding the answer with calorimetric methods. What we do have, however, is information for a couple other reactions. We know the information for that next reaction, the carbon monoxide plus oxygen to form CO2. We do know the enthalpy for that process. We also know the overall enthalpy for carbon plus O2 making CO2. So we know the enthalpy for the synthesis of carbon dioxide. So we know both of these. And so what this leaves us with is this is the reaction that we want energy information for. We want energy information for the synthesis of 1 mole of carbon monoxide. To get that, we're going to use the enthalpy information we have for carbon monoxide plus oxygen giving us carbon dioxide, and also carbon plus oxygen giving us carbon dioxide. So we have information for these reactions. We're going to use it to find the information for this reaction. And again, since enthalpy is a state function, we can do that. And so what we want is simply to find this one-step process. We want from carbon going to carbon monoxide. What we can do, though, is use this 2-step process, carbon to carbon dioxide, then to carbon monoxide, because either of these paths will give us the same value for delta H, since delta H is a state function. Let's look at an energy diagram that shows the same thing. And so this is an energy diagram for the 2 reactions that we actually have. We have information for carbon plus oxygen making carbon dioxide. And that releases 393.5 kilojoules. We also have information for carbon monoxide plus half of an oxygen giving us carbon dioxide. So we have energy information for this process here, and we have energy information for this process here. What we want, and especially this makes sense if you flip this equation here, if you flip this equation, then that shows us that what we want is energy information for this process. And so what we can do is we can recognize that to get to here, I can either go directly, I can either just do this, but this is the process I don't have information for. I do, however, have information for this, and I have information for this. So I have information if I follow this indirect pathway. I want to get to here. I can't get here directly to find my thermochemical data. I can go this way. Going this way, I now have to think about the reverse reaction of this, right? So we have information for CO plus half O2 gives us CO2. But if I reverse this, if I instead think of CO2 gives us CO plus half O2, and what have we talked about? What does that do to our energy information? Reverses it, right? And so to go from here, to get this information, I'm going to do this, which is negative 393.5. I'm then going to do this, which is the opposite here, so positive 283. Negative 393.5 plus 283 gives me negative 110.5. That is the essence of Hess's law. That I can manipulate equations that I have. I can manipulate thermochemical equations that I have in order to look at a combination of equations to get me to where I want to go. And so when we look at the rules of setting up a Hess's law problem, and this isn't going to make much sense until we do a few examples out together, which we're going to do quite a few. But the general steps are you manipulate your equations. You're going to manipulate your equations however you need to in order to get the products that you're looking for all on the product side, and the reactants that you're looking for all on the reactant side. And you need to manipulate things so that things that you don't want in your final equation cancel each other out. At that point, we can actually look at adding up our delta H values. At any time that we manipulate an equation, we have to perform the appropriate manipulation to the delta H values as well. And then we add everything up. So again, I know that doesn't make a lot of sense, but I like to list out the rules, what we're going to do. Let's look at an example now. So here we have two basic equations. We have an equation for 2H2 plus 2O2 in the gas phase, forming gaseous water. We also have the equation for gaseous hydrogen and gaseous oxygen making liquid water. So we know the energy information associated with those processes. What we want is the energy information associated with just water in the gas phase going to water in the liquid phase. And so this is the equation that we want. This is what we're looking for. This is our target equation here at the bottom. So the first thing that we want to do is we want to manipulate our given equations so that all of the reactants that we want are on the reactant side and all the products we want are on the product side. So we can see that we want 2H2O gas as a reactant. In equation 1, 2H2O gas is a product. So we're going to reverse that equation. We're going to flip that equation around. And remember that when we do so, that reverses the sign of our enthalpy. And so we get this. So now we have 2H2O gas gives us 2H2 plus 2O2, and that reverses our sign to now positive 483.6. When you do this, and when you see examples that I am going to post that I've worked out, in order to save yourself some confusion, when you manipulate an equation like this, I would literally cross out the initial one so that you know you don't have to work with that anymore. We've reversed it. We've manipulated that equation into a form we are going to use. So cross the one out that you're not going to use. Just get rid of it because we don't have to worry about that one anymore. We now have all of our reactants on the reactant side. So here's our target, has reactants of 2H2O. And so what we're looking for, or the equations that we have to work with, have that same 2H2O gas as a reactant. Our product is 2H2O liquid, and we have that in our second equation as a product. So that one's okay. The next thing that we want to do is look to try to make sure that we can cancel out anything that is not in our target equation. And so you can cancel out in these Hess's law problems, you can cancel out anything that appears in your given equations as a reactant and a product. And so in this case, we have 2H2 as a product in equation 1. It is also a reactant in equation 2. And so we're going to get rid of that. We also have O2 as a product in equation 1 and O2 as a reactant in equation 2. So we can cancel those out. And then we see what we're left with is 2H2O gas as a reactant and 2H2O liquid as a product, which are exactly what we want. At this point, now we know we've manipulated the equations in the ways that we need to. Now we can simply add up our enthalpy values. Positive 483.6 minus 571.7 gives us now an overall enthalpy of negative 88.1 kilojoules. And there it is. Now we have successfully used Hess's law to calculate the enthalpy of our target equation, and we did so by using two related equations. Let's go through another one. So in this example, we want the enthalpy information for zinc carbonate decomposing into zinc oxide and carbon dioxide. So we're going to go through the same process. And so we want to start looking first to get all of our reactants and products on the side that we want them to be on. And one thing that we see here as I look through these, I see that here in equation 2, zinc oxide is a reactant, but I see that I need zinc oxide as a product. So I'm going to reverse that equation. And when I do so, I'm going to reverse the sign of my enthalpy. And then I'm just going to cross that out. Sorry, it looks like my target disappeared from down below, but it is still up top. Next, I look at my third equation, and I can see that zinc carbonate is a product, but I do need it as a reactant. So same thing, I'm going to flip that equation. When I do so, I'm going to reverse the sign of my enthalpy. And so now I've at least got my major products and reactants where I need them to be. I also have in my top equation, I have CO2 as a product, and I have it as a product here. So it doesn't look yet like I have to do anything there. So let's see if we're at a point where we can start canceling things out and be left with what we're looking for. So we can see, for instance, sorry, I'm just looking through here a little bit. Oh yeah, there it is. Couldn't see my other H2CO3 staring right at me. And so H2CO3 as a reactant and H2CO3 as a product. So that can go. H2O as a product here and H2O as a product here. So I have two H2Os on my product side. I have two H2Os on my reactant side. So that can go away. I also have, zinc hydroxide here as a reactant and zinc hydroxide here as a product. So I can cancel all of those. What I'm left with is my zinc carbonate, my zinc ox as a reactant, and my zinc oxide as a product, and my CO2 as a product. So I've done all the manipulations that I need to. So then I can then add up my enthalpies, and I'm left with 17 kilojoules. Another example. This one's going to get even a little bit more complicated. And so we have our target equation up top. And so we can see from that if we look at our target equation here, I'm going to want C2H2 as a reactant. My first equation gives me C2H2 as a product. And so I'm going to go ahead and reverse that. I also went ahead and did the second equation. And so we can see that I need, actually, let me back up. So the other thing that I need is I need H2O as a reactant. I also, how do I want to explain this? So I'm going to need H2O as a reactant. Sorry, I need H2O as a product. But if we look through some of these other equations, I see that I am going to want two CO2s as a product. So this is where you've got to sort of go through it and really kind of investigate and go back and forth with some of this. But I want two CO2s as a product, which the third equation does give to me. But in the third equation, I've got three H2Os as a product. I've got H2O as a product here as well, only one. So if I can flip this equation, though, and get it as a reactant, and also double it, that would get me two H2Os as a reactant, and then I would have three H2Os as a product. So the H2Os on the reactant side would cancel, leaving me one as a product here. And so we're going to do that. We're going to flip the bottom equation and double it, leading us to positive 342 kilojoules there. We're now ready to cancel everything that is the same on both sides. I've got two H2s in my first equation here as a reactant, two H2s as a product, C2H6 as a product, C2H6 as a reactant. Here's my two H2Os. That's going to cancel out with two of these, leaving me with just one H2O here still. Sorry, what else is going on with this one? Oh, nope, nothing. Things just got a little bit messy because I didn't change my colors. Sorry. You can see colors actually help in these quite a bit too, because without changing some of my colors, then I just threw myself off a little bit. But the other thing that we can do is we saw that we had, where was it? We had half of an O2 as a reactant, half an O2 as a product, or one O2 as a product here. And if we look at all of our O2s, then those simplified down to 5/2 O2. And so that's another thing that we were looking for. Sorry, I didn't explain that very well. Let me back up on the O2s. I had 7/2 O2. Just so you can get rid of here we go. So I had 7/2 O2 as a reactant. I also have one full O2. My mouse is really bugging me today. I also have one full O2 as a product. So that one full O2 as a product can disappear. When I do that, that's going to get my 7/2 O2 down to 5/2 O2. And so that's the replacement here. But again, what this tells me, now that I've canceled everything, I look at what I have left, and everything that I have left is what I want in my target equation, which means that I can now add up my enthalpies that I have, and I'll be left with the actual final answer. Here are several to try on your own. Now, what I've done with these is you've got the problem here. You've got your target equation on the top, and you have the enthalpies of the various equations that we're going to use. And so apply that same process. What you want to do is go through and manipulate the equations however you need to, so that the products you're looking for are on the product side, the reactants you're looking for are on the reactant side, and everything else cancels out. Remember that whatever you do to an equation, you have to do the same thing to the enthalpy value. If you flip an equation, you've got to reverse the enthalpy value. If you double an equation or even cut an equation in half, then you have to do that same thing to the enthalpy value. And so go through these, see what you can do. I'm going to show you the answer to this first one in just a second. If you didn't get the right answer, then obviously go back on your own and see what you hopefully find what you did wrong. But I have also worked out my process to all of these, and I am going to post that on somewhere on the website as well. Maybe even just under the lecture on the lectures page on the website. That's probably what I will do. And so my worked out answers will be posted right along with the lecture, right on the lectures page of the website. And so pause the video now, see what you can do for this problem of carbon disulfide combusting with oxygen. See what you can get. Hopefully you came up with negative 1,075 kilojoules. Next problem. So go ahead and, same as before, pause the video, see what you can do with this Hess's law problem, manipulating these three equations to try to get our target. Hopefully you found positive 175 kilojoules. Next, pause the video. Hopefully you got negative 1755 kilojoules. And then a last example of a thermite reaction. Come up here in just a second. My mouse is a little bit laggy today too. Laggy and oversensitive. There we go. Oh, maybe not. There we go. So there's a thermite example. See what you can do. Oh, it's really acting up. There we go. For a final answer of negative 846.8 kilojoules. So Hess's law is not easy. It's definitely going to take some practice. And so, like I said, check out my worked out solutions to these. There's also lots of practice on the website. There's quite a bit of, we'll just bring that up real quick. There's quite a bit of Hess's law practice right on the Unit 2 materials page. You'll find not only some more worked out examples in the supplemental video, where I've gone through my entire process for several different examples, but then there are also some practice Hess's law problems down in the practice section. So quite a bit of practice to help you master these. So Hess's law is one way that we can go about finding the thermochemical data for a reaction that we can't measure directly. Another way is by using something that we call the enthalpies of formation. You can find these enthalpies of formation values in Appendix G in your textbook. And so you'll have quite a few problems in the homework where you have to use these. And so that's where you want to look, is Appendix G in your text. But the enthalpy of formation in general, and delta H sub F, it's the energy that's required to form 1 mole of a compound from its elements in their standard state. And this little degree symbol, by the way, just stands for standard conditions. And so this is telling us that when we find a delta H value, delta HF, then in these cases, it's just under standard conditions of like 1 atmosphere and whatever state that the element usually appears in at those standard conditions. The F just stands for formation. The delta HF of an element is 0. And we'll see where that comes into play in just a second. And so these are just some standard values of the heats of formation at 298 Kelvin, which is pretty much room temperature, standard temperature. And actually, let's just skip over that. I'm not going to even worry about that. Okay. So let's take a look at really what the delta HF values are giving us. And so let's look at each of these equations here. And so we want to write the formation from the elements of these compounds. And so for NaCl, when NaCl forms as a solid, it's going to come together from sodium, which would be a solid at standard conditions. Chlorine, remember, is Cl2. It's a diatomic. Chlorine gas under standard conditions to form NaCl. Now, we also have to recognize that NaCl only has 1 chlorine. Now, we don't balance this in the way that we normally would. Remember, normally we'd go 2 NaCl and 2 Na. Heats of formation, however, are given for, if we think about the definition of it, the heat of formation of NaCl is the enthalpy required to form 1 mole of the molecule. And so we have to have an equation that represents formation of 1 mole of NaCl, which means that we would have to put a half right here to balance this. And so this equation would represent the enthalpy of formation of NaCl. For part B, we would have carbon as a solid, H2, because a hydrogen is diatomic, plus O2, forming our C6H12O6. And then our balancing would look like this. And so this would be our thermochemical equation for the formation of C6H12O6. And so forth. I'm not going to do the rest of these, but this is what we're looking at. And so when we see the enthalpy value, for instance, let's just go back here. I think we had the enthalpy for, okay, H2O liquid in part E. Yep, okay. And so E, sorry, let me just come back to look at what that was. The value for the delta HF of H2O liquid, negative 285.8. And so what that really is, there we go. So H2 plus O2 forming H2O. And then we look to balance this. We would just have to have half of an O2. the delta H for that process is negative 285.8 kilojoules per mole. So that's what the enthalpy of formation stands for. It's how much energy is involved in the energy of the formation of 1 mole of that compound from its constituent elements. And the enthalpy of formation of an element in its standard state is always 0. And so, for instance, the enthalpy of formation of H2 as a gas is going to be 0. And that's just by definition. And we're going to use that. You'll see where we're going to use that in just a little bit. And so the way that we actually use enthalpies of formation to calculate the enthalpy of a reaction is we're going to take the enthalpies of all of the enthalpies of formation of all of the products and add those up, and then subtract that from the enthalpies of all of the enthalpies of formation of all of the reactants. This is another thing, another symbol. If you haven't seen, this uppercase sigma just means the sum of. And so as just as an example, I'm going to work through this worked out example of glucose in just a second. But let's say that we have a very generic reaction of 2A plus B makes 3C. We look up on a table, and so this would be like Appendix G in your book, but we can look up the delta H values of all of these compounds. And we look this up and we see that maybe A has a delta H value of, we're just going to use some simple numbers at first, maybe of minus 30. B has a delta H value of plus 15. C has a delta H value of minus 110. And so to find the heat of formation of this reaction, what we're going to do is add up all of the products. And so we always want to be thinking of products minus reactants for these. And so for our products, we have 3 times negative 110. That's all of our products. We're then going to subtract that from all of our reactants. A was 2 times negative 30 plus B, we just have 1 times a positive 15. And so if we then do this out, we get negative 330 minus that negative 60 plus 15, so negative 330 minus a negative 45. Again, we have to really keep track of our negatives here. But that's going to give us a final answer of, so we get negative 330 minus a negative 45, negative 285. These would all be in kilojoules. And so this would give us the final information then of this reaction, 2A plus B gives us 3C, has a delta H value of negative 285 kilojoules. And so that's a way that we would have, using these heats of formation, we're able to find the enthalpy of this reaction, even though we could not perform that directly. For whatever reason, we can't do calorimetry in order to find this, or we don't have a set of equations to use Hess's law to find the enthalpy of this reaction. But so we can use the heats of formation. So in our last example, we're going to look at we're going to calculate the heat of combustion for glucose. And so we want to know the enthalpy involved in this reaction. We have the heat of formation of glucose. We have the heat of formation of CO2. And we have the heat of formation of water. So let me back up. Why don't we have the heat of formation of O2? Because remember, by definition, the heat of formation of an element in its natural state is 0. So we don't have to worry about that one. And so what we're going to do here, there's a couple things that we have to recognize for this problem. First thing we have to recognize is our equation as it's written balanced? And it's not, is it? So we need to balance that equation because our process demands that we multiply our heats of formation by the number of moles that were present. Nope, that's a liquid. That's important for us. So to balance this equation, we're going to get a 6, and we're going to get a 6, and we're going to get a 6. And so we have to do that first. Then we're going to add up our products, add up our reactants, and we're going to subtract. And so in the case of CO2, so for our products, we have 6 times negative 393.5. For our products, we also have 6H2O. So 6 times negative 285.8. And so there's all of our products. Sorry. There we go. We're going to subtract that from our reactants. And so we're given the glucose at negative 1274.5. And then plus oxygen. Remember, oxygen was 0. Started to run out of space. And so we put all that into the calculator. And we come up with negative 2801 kilojoules. Let's see if that matches with the answer that I had. So again, just walks us through that we have to balance our equation. Negative 28.01 kilojoules per mole, because we did start out with 1 mole of glucose. And so that's how we use heats of formation in order to find the heat of reaction of a particular reaction. And so here's another example. And so we want to actually, in this case, calculate the standard enthalpy of formation. So we want the enthalpy of formation, in this case, of octane. We know the heat of combustion of octane to be negative 5440 kilojoules per mole. But we want to use that information plus the heat of formation of CO2 and water to calculate the enthalpy of formation of octane. And so in this case, what we're going to do it's helpful for us to first write out our reaction that we're interested in. Or sorry, it's helpful for us to write out the heat of combustion of the octane. And so remember, combustion reactions, so in this case, it's the reaction we have information for, C8H18 plus O2. So combustion reactions always give us CO2 and H2O. And then we balance this equation. We need 8, we need 9. What's that going to do to my O2s? Okay, sorry for that little glitch of the matrix there, but I just realized that I definitely want more space to write with. So we're just going to shrink this down a little bit more. Hopefully you can still see that. And I'm just going to erase this and start over so that I have more space to work with here. Okay. And so let's back up. Ultimately, what we want is the enthalpy of formation of octane. The information that we do have, however, is the heat of combustion of octane. And so let's write out, again, let's write out that equation for the heat of combustion of octane, C8H18. Combustion reactions involve oxygen and they create CO2 and H2O, and we're given delta H for that to be equal to negative 5440 kilojoules per mole. Then we need to balance this equation. And so we have 8 for our CO2 and 9 for our H2O. That gives me 16, 25 oxygens. And so I'm going to go ahead and put 12.5 O2s. Again, recognizing that it's okay for me to have these fractional numbers, especially because the enthalpy information that I was given was negative 5440 kilojoules per 1 mole, per mole of octane. So I need to keep this as a 12.5. And so there's my equation for the combustion of octane. Ultimately, well, again, what I'm looking for is the enthalpy of formation of octane. So we know that from what we just looked at, we can take the enthalpies of formation of our products, subtract the enthalpies of formation of the reactants. That's going to leave us with the enthalpy of formation of our reaction. In this case, we know the enthalpy of formation of the reaction. We want the enthalpy of formation, or sorry, we know the enthalpy of the reaction. We want the enthalpy of formation of one of the reactants. So let's set up our products over our products minus reactants. And so I won't put numbers in yet, but our products minus reactants is going to equal our negative 5440. So just like the example that we just did, only now we have the final enthalpy of the reaction, so we can put that in. And so the enthalpy of our products, 8 times our CO2 at negative 393.5. It's going to bug me. Not much better, Mr. Staples. But then plus 9 times the enthalpy of formation of our water, negative 285.8. And so there's our products. Then we subtract that from the enthalpy of formation of our reactants. That's what we're looking for, though. Because remember, the O2 is going to be 0. But the enthalpy of formation of the C8H18. That's what we're ultimately looking for. And we know this equals negative 5440. And so now all we have to do is perform the algebra, just perform the math to this. And so if we add our delta HF value to both sides, if we just add this to both sides and add this to both sides, then what we come up with mathematically is our 8 times negative 393.5 plus 9 times negative 285.8 plus 5440 is going to equal our delta HF of C8H18. We do that out and we get a magic number of, where did it go? Negative 280.2. And that is the delta H of formation of C8H18. Sorry about that little second glitch there. Matrix is glitching a lot on us today. Throwing a lot of 90s movies references at you this week, aren't I? Anyway. And so that is a lot of number crunching. That is a lot of just different thermochemical data, a lot of various processes to come up with our answers. But that is it for now. So again, do lots of practice. There are lots of practice problems in general on the website. Also on Chem 101, there's lots of different practice. but that is all for thermochemistry, which means that is all for Unit 2. I am going to post a little bit of a sort of a recap and wrap-up video for Unit 2, and I'll have that up actually just when this one comes up. Those will both go up at the same time. But that, again, that does mean we are done with Unit 2 with looking at stoichiometry and thermochemistry. So our exam will be coming up. So I highly recommend that you really start looking at that and studying for that if you have not already. And so take a breather, take a few minutes off. This has been quite a bit, but then come back and regroup and try a whole bunch of practice problems. That is it for me for today. And so I hope everybody does have a great day.